Uh, yeah, am I audible? Thank you. Yeah, thank you. Thank you so much, Simran, for inviting me to this session. And I hope all of you had a very happy Holi yesterday. Yeah, so without any delay, I'll just get started sharing my slides. It will be around our session, 1 hour session. And yeah, let's get started. And please don't forget to interrupt me in between if you feel any doubts. Um, I'll just go ahead and share my screen. Sure, sure. Um, okay. Is the screen visible? All right. All right. Yeah. So thank you everyone once again. And the topic is about trans-tokenization. It's a very interesting topic. A few months ago, we implemented this methodology. Um, it is inspired from a research paper written by two particular authors where we have also contributed. Uh, and we will talk about the problem, the challenges, and how we are implementing this in our own. So that's a little bit about me. I'm Shubhro, currently a machine learning engineer. I've published a few papers. Some of them are at the Scientific Python Conference, published last year. And I go by this ID everywhere in Twitter and LinkedIn. If you want, you can follow me. So the agenda will be we will talking about low resource language models, the trans tokenization, like the tokenization basic challenges and how to overcome them. Then we will be finally talking about the trans tokenization, the real solution, and the real world impact. Finally, we'll close the session with conclusion. And if you have any questions, we'll keep bandwidth for questions too. But you can also ask questions in between. All right. So let's talk about this topic. So this is monolingual language models. So what do you mean by monolingual language models? So these are a kind of language models that can only, speak or are maybe much efficient in a particular language. So it might be Hindi, it might be English, and anything. And monolingual language models you know, are very important in this world of AI because not everybody, uh, like not the 100% of the total tech consuming population use English as their primary language, and there are a lot of languages in this world that are very much underrepresented, and not much of that kind of a data is found in this world to train on those particular language models. So, you know, the high resource language models like GPT or BERT, they they focus on English. And what if I want to develop a very strong foundational model on Hindi or maybe something else, whose data is not available? So we will discuss about that topic today. As you can see that these kind of models like Robert 2023, they were non-English models, and they have already achieved a high performance. And these kind of models are really high in performance where they maintain the structure and the linguistic capabilities of that particular language. And also, the linguistic diversity in AI helps to preserve the cultural language. Now, uh, the challenge. What are the like the challenges in developing a low resource language model? So the main challenges in developing a low resource language model is data. So we will talk about uh, like the amount of data we need to particularly uh, train a low resource language model. Um, so you can see that if you want to build a language model that is based on these kind of languages like Assamese or Tulu or any kind of non-Latin languages. Let me also clear about something called non-Latin languages. So just for your information, non-Latin languages are those without the English alphabets. And so these kind of languages are Tamil, Telugu, etc. And these kind of languages are a lot, right? So if you know about pre-training an LLM, fine-tuning an LLM, so you will know that pre-training an LLM requires a vast amount of data so that the model can learn about, right? And there is a very big difficulty in sourcing this high quality training data for these languages. And these huge kind of data sets, they actually require trillions of tokens, um, trillions that we will come to an example, and I will make you understand uh, the vast amount of the number trillion. So this is a visual comparison of the data that is needed to train an LLM. So suppose one book. So even if you train the whole large language model on a single book, so that book contains around 40 to 50,000 tokens. So now 40 to 50,000 tokens is a lot of tokens, but that indeed is a very small number when we are comparing to trillions of tokens, right? Compare that to a bookshelf. You get around 2.5 million tokens where you have a lot of books, right? And for example, a single LLM training that you might require that takes around 6 trillion tokens, so which is equal to 2.5 million bookshelves. So you need 2.5 million of these to train your large language models. So this is like a visual comparison of how it should be, right? So given that is the problem, if you want to train your uh, LLMs on this amount of data, clearly that amount of data is not available for a lot of languages. And the point is, like, what is the solution for that? And so we come across trans-tokenization. So I hope you have understood the problem statements. If you have any questions, please feel free to ask them. And then I'll shift to the next topic. All right. I'll shift to the next topic then. Yeah. So the next topic is about tokenization issues, right? Um, when you will be using a large language model, uh, you will also come across the word tokenizer. And what is the basic functionality of a tokenizer is that it divides each and every word for you. It may be on the basis of subword or character level tokenization. It depends on the type of large language model you are using. So these kind of tokenizers, they actually separate and cut out the word for you, and then these are converted into tokens. So all these you see, these are called tokens. And then these tokens are converted into, embeddings, and and then further processed inside the large language model, and then you pass them through the layers of an LLM, and then you get the output, just to be that simple. But let's talk about the process of tokenization. How does tokenization work, and what what is its significance, right? So if you if you have an English tokenizer, let's consider this is an multilingual model like ChatGPT that has a lot of tokens. um, so it can speak multiple languages like English, Hindi, and etc. And it has, for example, an English tokenizer that is not well suited for the language you are using. So let's consider this sentence that I'm not a giraffe, this is an abstract thought. What happens is that when you use an English tokenizer, it divides it into a lot of um, tokens, right? So this particular example is from English to Dutch. This, as you can see, that this is an English sentence, and the things getting tokenized here are not English. So when you use an English tokenizer, and when you use when you use that particular tokenizer to tokenize different languages, that actually tokenizes each and every sentence into very small pieces where you lose the context of that sentence. So, for example, an English tokenizer that is tokenizing a Dutch sentence. So, this sentence just converted in Dutch. What happens is you get 23 tokens for this particular sentence. Why? Because this is not trained on the Dutch language. But the similar tokenizer, when you train this English tokenizer, sorry, this will be Dutch tokenizer, on the Dutch language, what happens is that you get fewer tokens. And that is something that we want to achieve. Now, the point is, why fewer tokens? Because, like, when your tokens keep getting larger and larger, you lose the context length of it, right? You uh, you need the attention layers to focus on each and every word and to predict the next token. And as your number of tokens increases, the computation increases. So what we want in a tokenizer is to compress highly dense information in minimum number of tokens, so that you can forward it into embeddings, and then through the layers of a transformer uh, of an LLM for further processing. Now, as you can see, when you train a tokenizer on the very particular language you want to use, you get less tokens. So developing a tokenizer is very important, hence. And next, we will talk about this particular solution now, so which is trans-tokenization. And trans-tokenization is that process where you don't need to kind of train a whole large language model from scratch for that particular language. What you need to do is, it is a kind of a knowledge transferring mechanism where you are transferring knowledge from one particular large language model to the other through a process called embedding mapping. And yeah, if you have any questions, you can uh, speak. Yeah, sure. Somebody has raised a hand. Okay, I'll just get back to the previous slide. Yeah, please, can you repeat the question? Oh, sorry. There has been a problem in the understanding. The point is that uh, we, I'm just putting out the English sentence so that you can understand. Actually, the sentence that is getting tokenized is a Dutch sentence itself. You're not using a tokenizer to translate from one language to the other. Tokenization is the process of segmenting these sentences using a particular norm. Now, I'm just putting this sentence so that you can understand the meaning of it in English. What we are doing is that we have already converted this sentence into Dutch, and that very particular Dutch sentence, we are using it across different tokenizers. So the first tokenizer is an English tokenizer, and the second tokenizer is a Dutch tokenizer. So, this is written English. Sorry for the mistake. So the second tokenizer is a Dutch tokenizer. Now, what is happening is when you are tokenizing a particular Dutch sentence with an English tokenizer, you get more tokens than expected. And when you are converting a Dutch sentence using a Dutch tokenizer itself, you are getting less tokens. And what is the point of having less tokens is that you can densely you can have more compact and dense information inside of single tokens instead of having a large number of tokens. And that actually helps you in the longer run, like in very long context lens. You need to reduce the number of tokens. Suppose one paragraph of a sentence. So in one paragraph of a sentence, estimate that there are 23 tokens and there are only 15 tokens to process. So which one will take less time to process? Obviously the one which has 15 tokens. So 15 tokens will get through the layers of transformer, through the LLM. Um, then you will generate like 15 embeddings. So obviously you're having less computation and it will be more faster. So that's the benefit. Now it depends on the tokenizer how densely you can pack information, right? Is the doubt clear? Great. Okay. Yeah. So if you have understood about the point, sure. So I'll just talk about this once more. The point is we are talking about creating monolingual large language models, and these kind of LLMs are generally those which speak in one language, and there is a need for these kind of LLMs. What we want to do is when you train these kind of LLMs on low resource languages, there aren't many data that is available on the internet. So we're talking about 6 trillion tokens, which is a lot. When you can see one book contains 50,000 tokens. So you need 2 million plus bookshelves to train on one data, on one language. So in comparison, when you have low resource languages, you generally do not have that kind of data. For example, the language of Bahasa or Tulu, right? You don't have that much of data. Uh, Tushar, do you want to ask some question?
I'm completely new to the concept. Is I will do my research upon it later. Tokenization is the currency used by AI tools for providing solutions. I've
Sorry,
just joined 5 minutes back actually.
sorry, I didn't get your question.
I will do my research on tokenization. If there's any link to any website or resource, you can share that with me. तो मैंने अभी अभी शुरू किया है समझना तो I got the point that one book is equal to 50,000 tokens. But what is a LLM training thing?
Okay, so basically the point is you are new to this field and you don't know about what is called tokenization, right?
Yes, yes.
Okay, great. Let me just go back and talk about tokenization. So, can you see this slide? So, what we're talking about tokenization is when you type something in ChatGPT. For example, let's take an example. When you type something in ChatGPT, what happens is uh, no, no, I am not a giraffe. This is an absurd thought. You suppose type this sentence in ChatGPT. What really happens? Let's get there. So each and every sentence, like each and every large language model, has their own tokenizer. Now, what is the function of a tokenizer is they break down the sentence into meaningful representation. Now, each and every large language model comes with their own dictionary. Okay, so what happens is that um, when you are writing no, I am not a giraffe, the word no is in the dictionary of the English language model. I am not a giraffe. All these words are inside the dictionary of that large language models. The work of the tokenizer is to create a meaningful relationship between the tokens that are broken down, and it should have a close relation to the dictionary. For example, giraffe word has a number representation of 002 inside the dictionary of ChatGPT. Now, the work of a tokenizer is to identify the word giraffe and then separate it out as a form of token. Now, if you have an English tokenizer and if you have a Dutch tokenizer, so just for example, English tokenizer is trained on English language, Dutch tokenizer is trained on Dutch language. Now, what happens when you try to tokenize a Dutch sentence with a English tokenizer? Because inside a Dutch sentence, like an English tokenizer won't have Dutch representations in the dictionary, right? So, what does the English tokenizer do? It basically converts each and every character, it assigns each and every character, the closest possible character, a number. Now, what actually happens is that you get a lot of tokens. Now, compared to that, when you use a Dutch tokenizer, when you use a Dutch tokenizer, it is already trained on the Dutch language. So it understands the meaning of these words, right? These are Dutch words. You can see the same word that is being tokenized by the English sentence are more. So the number of tokens are more. Now, you want to know like what are these tokens at the end of the day. So these things are getting converted into embeddings. Think of these tokens as numbers. So this is just step one. And then you need to convert these into numbers 001, 002, 003. And then you have this kind of attention mechanism inside the large language model when you compute the closest possible relationship with each word. So here I refers to so I am not a giraffe, and that is an absurd thing. Let's consider this sentence. What does that refers to? That refers to the word I am not a giraffe, right? So in terms of mathematical representation, what happens, the word that will have the closest possible similarity with this sentence, or maybe the word giraffe, right? So these two will be the closest possible, will have the closest possible relationship mathematically. uh, we can talk about the mathematics, but I think at the basic level, this is what I can explain, and later, if you want, we can go into mathematics later, which is a bit complex. But the point is, these tokens are getting converted into numbers, and then these numbers, are processed inside a large language model. After they are being processed, you get the final answer from ChatGPT. It's the response that comes out. The point is, the whole point of this slide is, when you are using a tokenizer that is trained on the language you are trying to use it for, the number of tokens are less. And what happens when the number of tokens are less? You basically have less compute. So number of process becomes slow, the model becomes faster. That's the ultimate thing. So did you get it, Tushar? Yeah, I think he's a bit confused still. Sure, sure. um so let's get back to the point where we already started from. We were talking about the final solution, that is trans-tokenization. Let's and also a small recap for each one of you that have joined recently. We're talking about creating large language models for languages that do not have a lot of data. We're talking about a whole library of data, or like 2.5 million bookshelves of data. So, what from our personal experience, we wanted to create large language models for languages like Tulu, Bahasa, and for which a lot of data is not available on the internet. What we did was this process of trans-tokenization, which I'm now going to talk in detail about. And what happens in this process is you don't need a lot of data for creating a large language model. What you need is embedding mapping, which is a very famous technique, and we're going to talk about now. So this is actually works like magic when you don't have a lot of data, but you still uh, are able to make a good quality large language model with whatever data you have. So what we do is you use a fine-tuned LLM that is already kind of trained on the source language. So there are two languages that you need. So one is a high resource language, and the second one is a low resource language. So what is a high resource language? High resource language is something which you have a lot of data for. Suppose English is a language that is high resource, and for example, Tulu is a language which you don't have a lot of resources for. Now, you need a large language model that is already fine tuned in English, and we will basically trans tokenize the English large language model uh, with a Tulu tokenizer. That's how it works. Let us get to the details. I'm skipping this slide because we already discussed a lot about this, but also I'm just going to talk about this little thing, creating tokenizer once more, because I just want you to know that how you can create your own tokenizer. So the first step of trans tokenization is to create your own tokenizer. Now, how do you create your own tokenizer? Creating your own tokenizer, for that you need the target language that you want to tokenize on. So for example, you want to make a large language model based on the Tulu language, and so you need to make a tokenizer for that Tulu language itself. And what are the ways of creating a tokenizer for that? So you need a data. first of all, data for that, parallel corpus data. We will talk about that. You need a tokenizer. Now, how to make a tokenizer? There are a few ways of creating tokenizer. So one is Google sentence piece tokenizer. You have Hugging Face tokenizer. You can use these libraries to create your tokenizer trained on your own small data. So we are only talking about very small amount of data, maybe 500 megabytes, right? So after you create your own tokenizer, uh, you have to basically uh, choose the type of tokenization that you want to do. So as you can see, this is a Bengali word, and this is getting word level tokenized. What is word level tokenization? Is that you tokenize each and every word. This is a bit complex, and also this is not more beneficial. The next one we have, which is state of the art, is subword level and character level tokenizers. So this actually uses subwords to create individual tokens. So if you see this word, there will be an underscore between this character and the following character. So that's how you do like subword level. And character level tokenization is that each and every character will be tokenized. Like you generally put an underscore there. There are many types of tokenization, and there are these are the following. And what happens is, what do you do with the tokenizer, right? So let's discuss there. So suppose you have this tokenizer, right? You already have this tokenizer which you trained on the parallel corpus. uh, just to tell you once more about the parallel corpus is the data which you prepare to train your tokenizer on. So if you are training on the Tulu language, you need to create a data with a parallel corpus where you have the English on one side and maybe the other language on the other side. Okay, somebody raised a hand. Sorry, I didn't see. Yeah, if you have a question, please. Uh, okay, okay, let's continue. So, for example, you created your own tokenizer, and now you have that same data, right? So this is step two of trans-tokenization and how it works. So you create another parallel corpus when you have the source language and the target language here, and then you use your tokenizer to tokenize both these sentences. So as you can see, these sentences are getting tokenized on the basis of any type of tokenization, word level, character level. So you tokenize them, and then you use a semantic translation tool called fastalign. So what does fastalign do? So you get percentage of translation for each and every language, and that process is called token mapping. So what you do in token mapping is that in the English language uh, and in the Dutch language, for example, you figure out how much of the sentences can you relate after tokenizing. So here is a very beautiful example. So this is a sentence called "I love learning," and this is the same translation of that sentence in Dutch, right? Now, what happens is when you tokenize both these sentences, you should be able to relate I with this word, love with this word, and learning and empty space with these two words. That's the magic of Fasterline, and that's how token mapping works. Now, when you get these token mappings, not 100% of the data, you're not able to map 100% of the data, obviously, because Fasterline only works statistically. It does not understand your language. So for example, in our case, we got 75% translation, meaning that if there are out of 100 sentences, we were able to successfully translate and find out the meaning from English to Dutch for only 75 sentences. So out of 100, 75. Now, uh, when you do that token mapping, so this mapped tokens, now we will take this mapped tokens and manually we will do embedding mapping. Now, what is the process of this embedding mapping? Let's get there. So embedding mapping is that you have these kind of sentences that are already tokenized, few, some, you, and these embeddings will be summed up, and then new vector representations will be created inside the target large language model, where you have the translated versions of this. So just for example, I has an embedding. Embedding, if you don't know, so tokens they get converted into embeddings like 001, 0026. These are numbers. And then fast align finds out the statistical relation with from I to this word. And once you find that meaning, this word's token will be this word's embedding will have a new vector representation in the translated form in this following large language model. Now, that's the magic. This is how you do embedding mapping, and it is done manually. And that's the magic. Like, you don't need any extra data for to teach a large language model the relation of a particular language, like how it is spoken and the linguistics capability of that particular model. So that's how you do it. And then you can use those combined vector representations to generate the corresponding tokens. So if you have any doubt in this embedding mapping, please let me know. So after you do this embedding mapping, your model is almost ready, and now you just need to pre-train it on, or you maybe you can fine tune it anything on the limited data you have. So just for our case, what we did, we trained it on A100 GPUs for 40 hours, and our model, with just limited amount of data, we were able to beat the base models of Mistral 7 billion parameter models. So that's like the whole process of tokenization. It has three big steps. So one is token alignment, for which you need to understand what is tokenization, what is embedding, how a large language model works. You need to use this tool called Fast Align, where you need to map tokens. And first of all, you need to create your own tokenizer using Google Sentence Piece or Hugging Face Tokenizer, anything. After you map your tokens, you need to do embedding mappings, wherein you take uh, the embeddings of one particular language and you manually do the vector representations of that in the other language. And after you do the after you map embeddings for that particular language, just for making it all clear, you need to do model adaptation. That is, just fine tune it on a small data, maybe pre-train on a small data. And yeah, that's how you do it. So uh, we can dive into the code just to, like, start trans-tokenization. You need 50% source and 50% target language, the one which I spoke about like a minute ago. So you need to choose the source model and the target tokenizer. You need to create the parallel corpus. You need to tokenize both sides of it, and you need to map tokens. And all of this, like map token mapping, embedding mapping, and just token mapping and embedding mapping, can just be done with pip install trans-tokenization. Trans-tokenizers, we made a library for that. You can easily use it. No need to do it manually anymore. And is my repository visible? Like, is this page visible? I don't think. I just click on the GitHub repository. Is the You can only see. link is there, but I just changed the page. You can't see it. You can't couldn't see it. Okay, okay, yeah, got it. Okay, I'll reshare in a minute. No problem. So I have the screenshot of a particular file here. So this is the whole library that we are talking about. So as you can see, um, you need to have your source model. So what we did, this was the Mistral 7 billion parameter instruction fine-tune model. And then you need to create your own tokenizer, the way I told you. So you need to create your own tokenizer, and then you need to have your aligned corpus. So your corpus should be like a parallel corpus in the target and the source language. And just pip install trans-tokenizers and it will do everything for you. Fast align will do the token mappings and etc. So yeah, that's about it. That's the whole Python file. So you get done with the three steps. So token mapping, embedding mapping, and model adaptation. You can use Unsloth AI's tool to basically fine tune. If you want multiple GPUs using PyTorch FSDP plus QLoRa, you can do it with Axolotl. And full fine tuning you can do with PyTorch, Torch Tune, and anything. So these are just some of the tools with which you can do fine tuning. And yeah, that's about it. And I'll be open to questions if you have. So this is like the most important part. These two slides are like the most important parts. um, yeah, and I'll be open to questions now. Simran, can you see that are there anyone raising hands or such? I just can't see from here.
No, nobody's.
All right. No, I have completed all the slides. uh, Usually getting a job in machine learning. So, so you're asking by applying these concepts, like what you want to do? Great. So from trans tokenization, you will be able to learn a lot of things. Uh, First of all, you can learn about the basic architecture of of a large language models, the 32 layers of a llama model, how it works. Um, then when you type in something to a chatbot, how it internally processes those tokens, how does a tokenizer work, and how do all the sentences that you are typing to a chatbot gets converted to tokens, and it further then gets converted into embeddings, and getting it passed through all the 32 layers of the large language model, all the 32 transformer layers of the large language models. um, Attention mechanism, how attention mechanism works. You will know the famous QKV formula, that the query key and value, the softmax of query key and multiplied by value, like how all of this works. Uh, then you can learn more about embeddings. how does embedding work in real life. You can uh, understand about the mathematical representations of the embeddings, and later you can learn about fine tuning, how does fine tuning works, and you can also learn about uh, the the different types of training of a large language model. So for example, there are pre-training, there is fine tuning, and inside fine tuning there are a lot of fine tuning methods. Like you have quantized low rank adaptation, you have simple low rank adaptation, and then you have like which comes under PEFT. So yeah, there are all sorts of things, and obviously I may have missed some topics, so there is a lot more. So yeah, a lot to learn. This was a research paper from which we did the practical implementation of it, because we wanted to develop foundational large language models for some particular languages where we did not have enough data to build a language model entirely by training it. So we needed some kind of trick, because, as I said previously, there are some languages where data is not available sufficiently on the internet. Hence, you can use these kind of technology. You can use this technique, this research methodology, and the the simple fact is that this is you don't require any kind of industry grade operating tools to implement this research paper and everything, because everything that I showed here, you can just do it. You don't need expensive GPUs to do it. You can just do it on the GPUs that you have in home. So that's the beauty of it. Yes. So, if you don't have a lot of data in Chinese, with the limited amount of data, you can create a large language model that is based on the Chinese language. Sure. And yeah, for that, you need, for creating a large language model with a low resource, from a low resource language, like based on a low resource language, you definitely need a large language model that is uh, already trained on a high resource language. So, for example, English and Chinese, if you say Chinese is a language that doesn't have a lot of data, English language should be there, and it should be trained on a lot of data. And then you basically build a Chinese tokenizer, and you map the embeddings from the Chinese language to the English large language model. So yeah, that's how it works. You don't need to have data. You don't need to have data in English. You need a large language model that is already trained in English, and then you can use this kind of uh, trans-tokenization strategy. Sure. So, like, shall I end the session, or like there are some questions? Did somebody raise hand or something? Can you see?
Hello. Yes, hello.
I think you're not audible, Ramesh.
Yes, have you got me now? Am I audible?
Actually, there is a lot of static in the background.
Okay, one second. This should be fine. Am I audible now? Yeah. Yeah. Thank you very much, Shubhra, and to you as well, both of you. Thanks for your time. And this is the first time I've ever got involved with any kind of AI or data science. I'm basically a Python guy on the Python stack. This is something new to me, and not new to me. It's a kind of a new presentation which I got from here, inspired to learn something new. If there is anything on the future course of any kind of presentations you are giving, please include me. And I'm giving you a big thank you for that, and big applause to you. Right. Great, man. Keep going.
Sure. Will you connect with me and
Yeah.
this is you
Done. One sec.
have any
As I said, I'm very much on the Python side with the microservices. I've not ever got into any kind of any even at a data level. Actually, it's more of a stack oriented or on the microservice oriented. I am actually for all 7 8 years. And now I'm interested in really jumping into after Shubra's presentation. Now I'm looking like to get engaged into so called. So that's how it is, frankly speaking. Yeah, I'm from Bangalore. I'm from Bangalore. Yeah, Mr. Shubra.
Yeah, I'm from Bangalore too.
Good, good, good. Nice, nice. I hope we catch up sometime. Right, sure, in person. Done. Thank you very much. I've noted down your number. I'll keep in touch, please. Oh, good, good
Thank you.
week.
Thank you. Pleasure,
Good
sir.
week. Have a good day. Good weekend. Bye.
no preparation.
Hello. Yeah, it's fine. What about you? No worries.
Thank you. Thank you so much. It has been a pleasure to present this. Thank you. Bye.